This lesson is for FST Lesson 2-4 on exponential functions. A function is considered exponential when the independent variable is an exponent. Our general equation that we typically use for exponential functions is ab to the x power. As students first look at the notes here, it may seem a little bit overwhelming, but it's simply three parts that they need to worry about. The first part is the number that doesn't have the exponent with it is considered the initial amount, or another way of saying that is the starting amount. Typically that number will be a population or a beginning balance in an account. The b value is referred to in general as the growth factor, but know that the growth factor may be increasing or decreasing the amount as we go. If the b value is a number greater than 1, it will be a growth situation or an increasing situation. If the b value is less than 1 but not negative, then it will be a decay situation, which means it's decreasing. The exponent is typically going to represent time. The only caution I have for students here is that usually the time will have a starting date. And typically that starting date will be the years after 1900 or some other designated starting date. Keep in mind that if the time or the exponent ends up being negative, that simply means that that time is happening in the past. Keep in mind that the b value, when it is in decay form, is always going to be greater than 0. It should never be a negative value. Other things about the growth factor that students need to know: so sometimes the growth factor is given in a word form, like for example, if something is growing by doubling. If something's doubling or tripling, the growth factor is simply going to be a 2 or a 3. 2 for doubles, 3 for triples. Many times the growth factor is given in a percent form. If it's given in a percent form, students simply need to remember to turn that percent into a decimal, and in a growth situation they should add a 1 to the front of it. If it's a decay situation, decreasing by a certain percentage, students should turn that number to a decimal and then do 1 minus that decimal. Graphically, when you're working with a growth situation, the graph will be a curved line called an exponential curve, and it'll go up from left to right. The a value, the starting amount, is where it crosses the y-axis, so that will be the y-intercept. This is also true in a decay situation. The only difference is this graph has been reflected over the y-axis, and that graph will decay or decrease or go down from left to right. It will also cross the y-axis at the value of a, or the initial amount. Keep in mind that when you're working with a problem involving half-life, usually of a radioactive element on the periodic table, the b value will be a half or 0.5. One last issue or item to go with the graphs of these two exponential curves is the fact that both graphs have something called an asymptote. An asymptote is what the graph approaches but never reaches, or never crosses, or never touches. For both of these graphs, the asymptote will be located right on the x-axis. So if you wanted to describe the asymptote, you would simply say the asymptote is on the x-axis. If you were trying to give an equation for the asymptote, you would say y equals 0. The reason for this is if you try to plug in any number you want for x, including positives and negatives, you will still never get a negative result. These graphs are never going to go below the x-axis because you're never going to get a negative result when you raise to a power. There are other key features about these graphs that students need to look up in their book from page 106. We're simply going to do one quick example with 3 parts to illustrate the ideas from today. I believe this is matching with question number 1 in the homework. The only thing I'm going to have students do here is go a little bit out of order. So let's read the question, and then we'll actually start with the second question here, and then go back up to B, and then finish with C. In 2008, the population of Ireland was 4,156,119, with an average annual growth rate of 1.13%. Assume this growth rate continues. Express the population P as a function of n, the number of years after 2008. So be careful here. This is them indicating that there is a starting date of 2008. So when we create our equation, we need the starting value, which in 2008, that's our start, and they give us that number of 4,156,119. Then we need the b value. Many times the b value is put in parentheses. If students forget to do that and simply put a times there, that's perfectly fine. The b value, if it's growing, is going to be 1 plus the percentage. Keep in mind that you take that percent and you turn it into a decimal first. When you turn a decimal into a percent, the decimal point moves 2 places to the left. Since we're missing a digit there, we would fill in a 0. So we'd end up having a 1 there because it's growth, plus 0.0113. So 1.13% as a decimal is 0.0113. Since we want it to grow, we need to add a 1 to the front of it. The n is the time, so we would simply say n there. Another option is to say n minus 2008. Now we're going to utilize that equation, and we should probably say what it's equal to. It's equal to the population of n. So now we're going to utilize that function or that equation to answer the other two questions. Estimate to the nearest thousand the population of Ireland in 2009. Since the starting year is 2008, we'd subtract those two to get our time. So in this case, the n value is a 1. We'd simply type in 4156119 into the calculator times 1.0113. Technically, we should raise it to the 1 power. Raising to the 1 power doesn't change the value, however, so we can simply multiply those two together. When we do that, we get 4,203,000, and that's our answer. Finally, for part C, to estimate to the nearest thousand the population in year 2020. So to get the time, we would subtract the beginning year, which is 2008. So our n value now is a 12. So we're going to utilize our same equation, and we're simply going to calculate with an n value of 12. Keep in mind that you would need a calculator to do this. If you don't have a calculator that shows all the steps as you go, you would do the 1.0113 to the 12th first, take your answer and multiply by the 4 million. When you type all that in, you should get approximately 4,756,000.